Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. Today's webinar will consist of a brief overview of both programs, followed by two technical presentations on tools to reduce or eliminate the use of hazardous metals in DoD weapons applications. First, Mr. Frank Campo and Mr. Mark Miller of the U.S. Army will present their work on developing the process of waterjet-based cavitation and its application to weapons to remove refractory metals. Their presentation will be followed by a Q&A session. Then Mr. Aaron Nardi of the U.S. Army Research Laboratories will summarize his work designing powders to support cold spray applications for coating deposition. Aaron's presentation will also be followed by a Q&A session. We will conclude the webinar with a longer Q&A featuring today's three speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and also provide it to you in your webinar registration confirmation email. If you are unable to download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you continue to have technical difficulties or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to have difficulties, just call into the conference line shown here. You may also submit a comment using the chat box, but please only use the chat box to submit comments related to technical difficulties. The Q&A box should be reserved for questions to the speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. We do encourage you to submit questions as you think of them. And when you submit your question, please make sure to add your organization name at the end of your question so that we can identify you during the interactive session. With that, I would like to go ahead and introduce Mr. Timothy Tetreault, who is the ESTCP Program Manager for Installation Energy and Water. And before joining SERDP and ESTCP, Tim worked at the National Renewable Energy Lab, where he focused on energy efficiency and renewable energy project development for the federal sector. Tim?
Thank you, Rula, and welcome everybody to today's SERDP and ESTCP webinar. ESTCP is the Environmental Security Technology Certification Program in which demonstrate innovative environmental energy technologies. These investments capitalize on past investments under SERDP and other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring in the lab in pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in SERDP and 5 in ESTCP. Installation, Energy, and Water program area is only an ESTCP program, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapon systems and platforms, both SERDP and ESTCP programs managed jointly by a designated program manager. Today's webinar presents results from research and demonstration efforts that were conducted under the Weapon Systems and Platforms program area, which has essentially 5 major focus areas: surface engineering and structural materials, energetic materials and munitions, noise and emissions, waste reduction and treatment in DoD operations, and lead-free electronics. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, including munitions, mobility, and burial in underwater environments, managing AFFF impacts, assessments of commercially available fluorine-free firefighting foams, pathways under non-stationary conditions and their implications for wildlife and human exposure on DoD lands, and finally, the abiotic degradation of chlorinated solvents in subsurface environments. You can find additional information about upcoming webinars at this link. I'd like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would also appreciate if you can please take a moment to complete a survey that will pop up on your screen at the end of the webcast. And finally, I'd like to remind you that registration is open for the 2020 SERDP and ESTCP Symposium. This is a 3-day virtual event showcasing the latest technologies that enhance DoD's missions through improved environmental and energy performance. With that, I'll hand it over, and I hope you enjoy today's webinar.
Thank you so much, Tim. It is now my pleasure to introduce our first 2 speakers, Mr. Frank Campo and Mr. Mark Miller from the United States Army Combat Capabilities Development Command Armament Center, Bennett Laboratories, which is located at the Waterjet Arsenal in upstate New York. At Bennett Laboratories, Frank serves as a multidisciplined electronics engineer, and he works on the development of innovative solutions to modernize and provide environmentally sound technology to the DoD manufacturing base. Frank has co-authored over 10 journals and other technical publications on the topic of refractory metal coatings or coating deposition processes. He is the recipient of the 2019 U.S. Army Combat Capabilities Development Command Science and Technology Award for Waterjet Modernizing Manufacturing Weapon Systems Processes. Frank has a bachelor's degree in engineering from the State University of New York Polytechnic Institute and a master's degree in business administration and finance from Rensselaer Polytechnic Institute, also in New York. Second, this presentation will feature Mr. Mark Miller, and Mark is a project and program manager focusing on the development of environmentally sound refractory metal coatings and coating deposition processes to improve gun barrel and weapon systems performance and life. Mark has co-authored over 30 journal and other technical papers on these topics. He received the SERDP Weapon Systems and Platforms Project of the Year Award recently for his research on chromium elimination and cannon life extension, and also the Army Research and Development Achievement Award for his work on explosive bonding and machining technologies. Mark holds a bachelor's degree in chemical engineering, a master's degree in materials engineering, and a master's degree in business administration and finance from Rensselaer, my apologies, Polytechnic Institute. Mark, can you please proceed?
Yes, thank you very much for that introduction. And good afternoon, everyone, and thank you for joining us for our SERDP and ESTCP webinar. And I'd like to give just a brief demonstration of the 4 programs that we've had dealing in these refractory metals and environmental coatings on weapon systems, starting about 10 years ago. The first one, as you know, there's a big need to do away with chromium, which is the conventional coating that is put on weapon systems. But chromium has some significant drawbacks. Obviously, it's a huge environmental issue. It's a known carcinogen. And secondly, it's also barely meeting today's requirements for higher energy propellants. As the propellants get hotter, the chromium is starting to fail. So for that reason, the environmental reason and the performance reason, there's a big need to start looking at other much higher melting temperature refractory metals. So we had a SERDP program about 10 years ago that actually developed the technology to put other metals, much higher melting temperature metals like tantalum, onto the inside of weapons. And then that transitioned into a ESTCP program where we actually demonstrated and validated on large caliber, full length, medium caliber weapons. Its performance was outstanding. It was more than 4 times the life of conventional chromium. And then it became apparent that there was a need to learn how to machine these new refractory metals because conventional machining methods do not work. And that led to our 3rd program, which was our second ESTCP program, which is the green machining of these weapons using water technology. And that developed into the current program, which Frank will talk about, using Waterjet for strip coatings off weapon systems. And then I'll give, Frank will talk about the technical progress we've had for this program, which just started, and then the conclusions and the benefits to the DoD. So I'm not sure how much familiar you are with Waterjet, but Waterjet technology is a very good technology to use on weapon systems, especially for things like cleaning the coatings, stripping coatings, or even rifling coatings. It's a green process. It's environmentally friendly. It's as simple as it gets. It's water and garnet, and just by things like standoff distance and the pressure, you can actually control how much material is removed. People think of Waterjet as, job shop type things. It's, there's thousands of them across the country, but what most people don't realize, Waterjet can be used for precision milling and to control depths and control surface finishes. And that's what we've developed with these SERDP and ESTCP programs. So going back to our first program, which started about 10 years ago, explosive bonding is a process where you put a donor tube, that's the orange in the area you see right there. You'd put it inside a weapon. You'd fill the donor tube with a proprietary explosive. You'd ignite it, and it literally would fly down the gun tube and weld itself to the inside of the gun tube, creating a nice thick liner. And this liner could be whatever material you wanted, whatever refractory metal. So we did this on full-length medium caliber weapons. We then took these weapons out to both Yuma and Aberdeen and fired them side by side next to the conventional chromium barrel, and the results were just outstanding. The weapons that we put the refractory metals on had more than 4 times the life of the conventional chromium coating, and with about 1/3 the wear. Some of the tubes we fired, even after 4 times the life, we couldn't condemn the tubes. That's how well they held up. This next slide basically shows you looking at the inside of the barrel fired, many times. The explosively bonded liner was barely worn out after so many rounds, and then the chromium tube was condemned. I believe, I don't know, the round count was 3,000 or so where it was condemned. It then became apparent, though, normal machining mechanisms will not work with these refractory metals. We were machining these these medium caliber barrels using 2-point cutters, as you see there. And this is nothing that you could do in production. It was just so we could rifle the barrel and test it. Normal broach cutters will not work with these refractory metals, so we had to develop a way to rifle these barrels if we ever wanted to use this in any kind of production environment. And so we, with the aid of ARL and Big Champagne, helped us submit sievers to actually put this out to the industry, to who could develop a waterjet technology to rifle these barrels. And we were quickly able to determine that very easily we could get to controlled surface depth and control the widths and surface finishes. And the waterjet could cut through anything. It doesn't matter if it's glass, what refractory metal is. Whereas the normal broaches can just do steel, the waterjet can pretty much do any material there is. And you can see in the photo there on the far right, we were able to do, it didn't matter if there was a twist, a progressive twist or whatever the twist was, the waterjet had no problem rifling the barrel. This just shows you some of the smaller caliber and medium caliber weapons that we were able to use waterjet rifling for. We fired these barrels. They actually performed, accuracy was better than the conventional barrels that were used with the conventional broaching methods. And that led us up to our new program that we're working on right now is now using this waterjet to remove coatings from weapons. And I'm going to let my partner, Frank Campo, talk about that. Go ahead, Frank.
Mark, I lost my screen and the network is down. You're going to have to finish it.
Okay, well, okay. We're right now taking this waterjet technology and we're developing it to now strip coatings from the inside of gun tubes. The reason that's important because there's technologies coming down the pipe that are putting these refractory metals on, and there's needs to be able to take these coatings off in an environmentally friendly method. Traditionally, a weapon system that's been chromium plated has to be reverse electroplated, which is another environmentally unfriendly process, and you can only do it once. So the waterjet technology allows you to quickly strip the coating off and then you reuse the barrel for whether you're putting a refractory metal other than chromium or chromium, and it allows you to just take the coating off without any problem. And the other methods that we're using for waterjet, the weapon systems may have whatever residue on them, whether it be the steel or the chromium coating, and it's absolutely essential that the tube be clean before any kind of process where you put on a refractory metal, whether it be chromium or any other process. And the waterjet can easily clean these surfaces before another coating is put on. And we've demonstrated that on several barrels now. This next slide basically shows this was an explosive bonding coating where we needed to take the coating off and demonstrate that we could take it off, and we were able to strip the coating off using waterjet technology. The surface finish on this particular coupon that you see was not what we needed, but we would just do a quickly finished hone to get the surface finish that's required for the gun barrel. So again, demonstrating that waterjet stripping can be used to take coatings off weapon systems. The other things we're able to use waterjet technology for is the waterjet honing, because traditionally after you put a coating on a weapon system, it's required that you hone the gun barrel to get remove a lot of the material to get the surface finish you need. And we were able to use waterjet honing to improve the surface finish tremendously after your process put whatever refractory metal you're putting on a weapon system. And this is just a truncated section where we waterjet honed the barrel and improved the surface finish tremendously. And again, this prevents the barrels from having to be reversed or replated or using any solvents or chlorinated paraffin lubricants where you're using machining processes to strip the coating, which is traditionally done. The waterjet process is an environmentally clean process, and it just really makes sense to use. The next step would be to actually scale this up into a full-length, to do full-length weapon systems, where you would have your weapon system would be put, on some kind of conveyor, and then you would put the water jet down the center and just strip the coating or whatever you wanted to do with it. You could actually rifle it if you wanted to, but it would be perfect for water jet stripping. And this just conveys just a simple model how you would use the water jet to use on a full-length weapon system. So we've demonstrated easily that the water jet technology can be used to improve the environmental aspects of any weapon system. It reduces the weapon system operations and costs substantially. Conventional weapon systems to machine, millions of dollars in the water jet system. Once the sunk cost of buying the system are really minimal. The water jet nozzle which is the only part that really wears out, is a fraction of a cost of normal conventional approaches or weapon systems components that are used to machine the gun barrels. We anticipate many other numerous applications for water jet stripping and technology as the future shows. Other materials will be coming down the pipe. Much higher melting temperature refractory metals will be coming and down the pipe for to be put on the large caliber gun barrels. Frank, can you want to talk about the sustainment and the life cycle costs?
Yeah.
Or?
Yeah, absolutely. One of the key parts of our ESTCP program is to conduct a sustainability analysis. And if you look to the right, the three circles, we want to minimize life cycle impacts, minimize life cycle costs in weapon systems, and what we're attempting to do is modernize and exceed performance requirements that we currently have, for at least in the manufacturing, and meet at least the criterion that we have for weapon systems performance. So the three key takeaways for our sustainability and alternative technology is obviously to modernize manufacturing, strip clean weapons using water, and support all Army systems, and hopefully transition this with Navy, Air Force, and make it a true purple program. There's some sustainability analysis guidance. There's a link below. It should work. If it doesn't, please contact me. Advance the slide.
Okay, and then, yeah, there's the last slide was the modernization and sustainability. I'm not getting that. I'm sorry. Yeah, the DoD modernization and sustainability. Secretary of Defense memorandum to do away with, to try to minimize the use of chromium as much as possible. And this certainly the first explosive bonding program met that. And you want to talk about the EPA guidance on reduction of, the paraffin?
Yeah, EPA was initially involved in asking for the reduction of short chain chlorinated paraffins in metalworking fluids in industry, and also DoD. Of course, at a weapons plant, we certainly use a lot of those, and this technology avoids the use of those. Certainly, one of the key Army modernization priority is long-range precision fires, and being in the cannon making industry, that's one of our main concerns, is to support the priorities of the Army. And again, we may extend life cycle of weapons and deferring deposition by keeping things clean, because we can also clean barrels of residue, which would certainly extend the life, and also have in-process inspection.
Some of the acknowledgments, I just want to thank, Ormond, who's doing a lot of our developing a lot of the water jet stripping with us. VRC Metal Systems, who we're working with, and I think you're going to hear from Aaron Nardi next. We want to thank Aries, who did a lot of the earlier work on the machining of the explosive bonded barrels, LTC for their laser bore inspection system, High Energy Metals, who did a lot of the explosive bonding work, and NAFC and Benet Labs as well. And that's for additional information. There, you can go to the SERDP website, and they have much more details, and reports are available for all 4 of our programs. But there are final reports available for our first 3 major SERDP and ESTCP programs that are available to anyone who wants them.
Wonderful. Thank you, Mark and Frank. We've received a number of questions for you, but before we get started, I'd like to remind our audience that you can submit questions by using the Q&A box on your screen. So we'll start with a series of questions from the Naval Postgraduate School. Maybe we'll start with you, Mark, and you can pass it on to Frank for additional comments. Does the Waterjet technology use only high pressure water, or is there an abrasive in the jet? And if using an abrasive, can different abrasives be used?
Yes, it is Waterjet and an abrasive, and you can change the abrasive, and different abrasives will give you different surface finish. It depends what you're looking for, how much material you want to remove, you know, how concerned you are about the surface finish, but most definitely different abrasives are used.
Thank you so much. Frank, maybe you can take this question from the Florida Department of Environmental Protection. What are some of the other refractory metals that are used to replace chromium?
That we're going to have to talk offline. I can certainly address that if they contact me directly or Mark on our contact information.
Great. So on the screen right now, there are phone numbers and email addresses for both of our speakers for the details. You can refer to this webpage or call Frank and Mark. What were you saying, Mark? I apologize.
Well, I mean, you look on the periodic tables, all the ones that have higher melting temperatures are viable candidates. And what's difficult about, I don't know if people realize that the reason chromium was conventionally used, because chromium is the only refractory metal that's soluble in water. So you can just like table salt, you can chromium oxide, you put it in water and it dissolves. And if it's soluble in water, you can electroplate it. The problem with the other refractory metals, which have much higher melting temperatures, they're not soluble in water. So therefore, they require these very advanced processes to get them onto a steel. Processes like explosive bonding, processes like cold spray, processes like sputtering, molten salts. Those are all processes that were developed for a need to put refractory metals onto a surface. Chromium is just used because it's the only one that's soluble in water, and you can electroplate it, but you cannot electroplate the other refractory metals. And so that's why these processes like explosive bonding are developed.
Great, thank you. This is a question from the Canadian Department of National Defense. You refer to SERDP. Can you please elaborate on this acronym and the challenges that it poses during, in weapon systems?
Frank, that's the chlorinated paraffin. That's your...
Yeah, it should be SCCP, short chain chlorinated paraffins. And what happens is that they're required in machining. The chlorinated portion of the lubricant activates at a certain temperature, and then the cutting of the metal becomes more effective. And this has been used for over quite a few years. Unfortunately, it's not biodegradable, and in cases in the past, it has been detected in the water stream. So this is one technology that we can certainly move away and avoid the use of the chlorinated paraffins.
Great, thank you for elaborating. This is a question from the University of Southern California. What accuracy and precision were you able to achieve with the waterjet machining?
Okay, and I'm not sure what they mean by accuracy and precision. You mean for the weapons we fired afterwards, or we have the guns or the weapon systems have to be machined to high tolerances, and we can have to talk offline about what those tolerances are, but the waterjet was able to meet all the same tolerances that the normal machining methods were able to meet. And they are extremely high for a weapon. You can imagine they're very high tolerances.
Excellent. This is a question from Lockheed Martin. Do you need to treat the water for the waterjet process using reverse osmosis? Will you need a chiller system? And what is the cost to set up and run a line?
I can briefly talk about that. Depending on your water quality of where you're getting it from, you have to do an analysis, and obviously the critical parts are nozzle buildup and pump life, because you're creating pressure by either reciprocation or a other type of intensifier. So depending on your water quality, you have to have a sunk cost. And again, you may need refrigeration depending on if you're going to, say a normal water jet system, you recycle the water. In our case, the flow is so little, we can simply put it through our waste treatment plant because we have a very, very low flow per minute.
Fantastic, thank you. This is a question from Sugino Corporation. What kind of range of water pressures is needed to strip the coating?
Well, we have to talk about that offline. If you certainly contact me, and you have a need to know, we can talk about that.
Thank you so much, Frank. All right, this is another question related to the waste that could be generated. One of the challenges we've seen is the amount of abrasive media waste generated for large parts or high volume parts. Have you addressed this? And can the media be filtered and reused before it degrades beyond useful levels?
Yeah, bingo, that's a great question. And we are fortunate enough to be located next to the Barton Garnet line, which has a recycling program at their facility about 40 miles away. So all of the garnet we currently use in our other processes are fully recyclable. What happens is if you start out at a rough grit, they bring it back and reclassify it for a finer grit at the Barton plant. So it can be at least reclassified once, if not twice. So what we do is send all the material up to the Barton plant, and everything gets recycled.
Fantastic. All right, this is a question from Siemens. Are there any cases where it is more cost-effective to use simulation to predetermine or select proper abrasive materials to apply? Frank?
Great question. We are in like the second year of this is the second year of our program?
Yes.
And that would be something we like to look at. So maybe Siemens can give us a call or send us a message, and we can talk to them about using that technology and modeling software if they have something like that.
Fantastic. Thank you so much. This is a question from Luna Innovations. Have you conducted any tests on the newer coatings regarding the effect they have on crack growth rates?
Well, we've done, go ahead, Frank.
Yeah, that's another great question. And in our program, we've certainly done a lot of work with the explosive bonding program utilizing both EDS and SEM technology, scanning for material characterization. And I think some of those results are in the ESTCP final reports. Is that correct, Mark?
Yeah, we've looked at everything, but I can tell you that the crack growth rates were a lot less with the newer coatings than they were with the conventional chromium coatings. And these weapons withstood extremely aggressive firing scenarios. Extremely. Some of the hottest propellants ever used for the medium caliber community were tested, and the refractory metals held up outstanding compared to conventional chromium coatings.
Great, thank you, Mark, and thank you, Frank, for a great presentation. Just a reminder that you can download their final report from their SERDP and ESTCP webinar webpage. We're going to get back to some of the remaining questions that came in for Frank and Mark during the last Q&A session, but at this point, we'd like to go ahead and transition to our third speaker today, who is Mr. Aaron Nardi. Aaron is the team lead for the Combat Capabilities Development Command Army Research Laboratories Cold Spray Center and affiliated laboratories, where he leads all aspects of material processing, equipment design, and process parameter development for projects related to cold spray. Aaron has over 40 patents related to cold spray, advanced manufacturing processes, erosion protection, wear-resistant coatings development applications, coating structures for fatigue mitigation, and components. He received a bachelor's degree in mechanical engineering and materials sciences from the University of Connecticut and a master's degree in mechanical metallurgy from Rensselaer Polytechnic Institute in Troy, New York. Rensselaer is a very efficient university for graduating all three of our speakers today. So Aaron, at this point, we're going to turn it over to you. Please proceed.
Okay, thank you very much, Rula, and thank you all for joining us. The process I'm going to be talking about is cold spray deposition. So we're transitioning from material removal to material deposition. Similarly, we're talking about a very high velocity nozzle type approach to depositing materials. I'm going to show you a little bit more about that. And these two technologies are very compatible in that we're working very closely with the folks at Benet to deposit specific materials that are then water jet machined to achieve a wide variety of goals. So to go on here, let me tell you where we're going. We're going to be talking a little bit about the process itself, the physics of the process, how consolidation occurs, and what the effects of that consolidation process are on the mechanical properties. I want to talk a little bit about some unique materials that we've developed specific to SERDP and ESTCP. And then I'll end talking a little bit about a couple different types of equipment and some new equipment that's being developed for deposition of materials using cold spray. So the cold spray process uses, as I said, a nozzle. This is a converging, diverging nozzle. Instead of liquid in the water jet, we're using a compressible gas. So that means it's a choked flow nozzle. The throat of the nozzle, which is the smallest section, is at Mach 1. As we expand that gas beyond that, it rapidly accelerates towards the target, where it impinges at ballistic velocities and bonds. We'll get a little bit more into that. In order to enhance the performance of the process, we do things like heating of the gas or using alternative gases. So instead of using air or nitrogen, we might use helium, for instance, which has a much higher Mach number and can achieve much higher velocities. So if we look at the process itself and the steps to achieving a bond of a particle on a substrate, the first thing that happens is we create a shock wave. So as that particle hits, there's a compressive zone created, and that creates a shock which actually ejects material from the interface between substrate. Then the material starts to deform, and during that deformation process, there's a lot of heat generated. So we plastically deform. As you can see in the images here, you see a lot of plastic deformation right at the interface between the particle and the substrate. That tends to localize. Due to that heating, you get more and more plastic flow at that interface, and the combination of the ejection of material from the interface and then those high levels of plastic flow give us the bonding that we're looking for, which is a cold welded bond. So let's take a look at the process itself, the impact process. We collaborate with many universities around. This is work that was done by MIT. You can see the images in the top of a particle impacting below what we call its critical velocity. So critical velocity is that velocity that's going to achieve bonding. And you can see that the particle in these time steps along the image hits, impacts, and then begins to rebound. In the second, you can see that the same particle now impacts, but as it's impacting, this is at a higher velocity. As it's impacting, you can see ejection from the interface, and then the particle stays in place. So again, what we know about this process for sure is that we achieve both a shock wave which ejects material from the interface, which is shown in Hassani's theory off on the bottom left, and then in the Asadi theory, we also know that we get strain localization due to the plastic deformation at the interface between the particle and the substrate. And both of these are very important for bonding. So now, exploit these two by changing the properties of our powder relative to our substrate. So we want to achieve high deformation in both the particle and the substrate, and we can add mixtures of materials, and we can change the material constituents in the bonding layer, for instance, and then grade out to a different layer in the structure of the material. So when we do this, we can start to achieve very high bond strengths. You can see the first one is aluminum repair for magnesium. This was done as an ESTCP program back in the mid 2000s, which ended right around 2010. This program showed that we could actually get structural properties out of the material that was deposited onto that magnesium. We actually got 22 KSI bond strength in this case, and when we failed the samples, we were actually pulling out pieces of the magnesium from the substrate. So now you can carry structural loads across that interface. There's several other examples of a wide variety of materials that have been tried and with very good success. Obviously, if we have this good of a bond strength, we need a test that can evaluate that bond strength. We use this one called lug shear, which is a buildup process. It's basically a die that is used to shear a lug of cold sprayed material from a substrate. All right, so now let's look at the interparticle bonding through the rest of the structure. I got two case examples here. One was a lower velocity nitrogen sprayed material, and one was a higher velocity helium sprayed material. The nitrogen sprayed material, however, was also a high temperature. So the amount of deformation in the particle was very similar. But in this particular case, what you can see is, and this is in the images in blue, you can see that the amount of substrate deformation is significantly different. And because of this, the bonding particle to particle is not necessarily going to be as good. So if we want to take a look at some actual results from that same case study, you can see, again, the helium is on the left, nitrogen is on the right. The tensile performance, we see much more ductility in the helium than we do in the nitrogen. And then when you look at the fracture surface, you can see transparticle fracturing of the helium sprayed material versus the nitrogen sprayed material. So this is showing you that that velocity is very critical for causing that interparticle bonding. Taking it one step further, those interparticle defects can also drive fatigue failures. So if we look at, in the bottom right here, we can see three SN curves. These are strain life curves, or stress life curves for a coated material. So the entire sample is made of this cold sprayed material. And we can see that a deposit that had 2.5% elongation here versus a sample that had 3.5% elongation and then 4.5% elongation had progressively increasing fatigue performance and approaching wrought material, which is out here. So these defects not only affect the ductility of the material, but they also affect the fatigue performance of the material. We can also measure the number of defects in our material by things like electrical conductivity. Here's an example where we have electrical conductivity of 6061. These are cold sprayed 6061, and this is wrought 6061. This is conductivity along the x-axis, and on the y-axis we have plastic strain to failure. So you can clearly see that the relationship, the correlation between these parameters. On the right is an example of copper, but here we have a wide variety of gases. We have air, nitrogen, and helium all shown on the plot. And you can see clearly that increasing velocity, either through increasing temperature or changing of the type of gas that we use, can significantly increase the conductivity of our material. So now let's talk about specific materials for nickel and chrome replacement. This is our ESTCP program and our SERDP program prior to that, where we developed materials specific to elimination of chrome and nickel. These are some of the materials that we developed. They include nitrogen and helium sprayed materials. Where performance of these materials relative to chrome is very good. On the left, you can see comparisons with a steel counterfeit. So it's steel on the coating. And both our lower hardness material, which is a mechanical blend of powders, as well as our WIP, what we call WIP W1 material, which is our highest hardness material, both outperform the chrome plating. On the right, you can see a study of abrasion resistance. And again, the red line is our WIP W1 material. And then the black and the green are two different types of chrome plating. So obviously there's variation in plating depending on the vendor, and we're showing performance better than both. We did a wide variety of studies of pressure temperature conditions as well as different nozzles to come up with a variety of potential spray conditions. And now we can start to apply this to different applications. One application is for armor repair. We looked at this WIP C1 material, which has a little lower hardness, but it's a very high impact resistant material. And you can see that comparing to the baseline, both nitrogen sprayed material and helium sprayed material performed equivalent to or better than the baseline steel armor that we're repairing. And finally, with respect to these materials, we're looking at rollout of them into the industrial landscape. So here is our development of production supply base for these powders. On the right-hand side, this is the type of work that we do to enhance the performance of materials. We blend things, we granulate things, we do heat treatment and sieving and so forth. And we've established suppliers who can do this with a wide number of different primary powder producers. So we're not locked into any one primary powder producer. Wherever that powder needs to come from, it can come from, and we can process it in such a specific way in order to make it cold sprayable. All right, so now I'm going to talk about equipment. There's high pressure cold spray, low pressure cold spray. These are kind of general categories. With high pressure, we're talking 100 to 1,000 PSI. With low pressure, we're talking about maybe 50 to 250, depending on the system. This is, these are some of the low pressure systems. I'm going to skip on to this chart, which kind of describes the impact of all of those various pressure conditions. So if you look at the chart here on the right, you can see that they overlap significantly in this low pressure, lower condition range. So all of the systems can produce the same coat in this range. There's only the high pressure systems, however, that can go out to these higher pressure, higher temperature conditions. And the implications of that are, here's an example of two different systems with a case study of 6061. The velocity range that's achievable with one of these systems is about half of the peak velocity that's achievable with the high pressure system. And as I explained before, those high velocities are what give us low defect concentration in the deposits and very good performance. With that high pressure capable system, we're also able to use smaller nozzles, which allow us to create ID nozzles, for instance. So in this case, I'm showing some examples of nozzles as small as 3/4 of an inch, which can then coat the inside of a bore that's as small as 1.6 inches. There's a variety of other nozzles that have been created for aluminum and for some of the refractory metals. So we have a large capability because of that wide window of operation of the system. And the last thing regarding equipment is we're building a system as part of an OSD Mantech program, which is, we're calling it a mobile hospital. In this case, it's a 2-connex setup that includes an entire cold spray manufacturing cell, as well as all the auxiliary equipment needed to operate that cell. So with a 2-connex setup, you can drop it at any forward operating base or airstrip or even a depot that doesn't have the equipment on hand, and then they can operate the equipment for whatever period of time to fix parts, and then it can go away and go somewhere else. So with that, I'll just throw up a few success stories. I'll be happy to talk about any of these in more detail. Wide variety of materials, from the harder nickel chrome replacement materials to bronzes and aluminums and so forth. So cold spray as a process, we can do a lot of work with this high pressure cold spray. It is very capable of depositing our wear materials that we've developed, as well as some of the thermally resistant materials that that Frank and Mark were discussing. And the quality of these materials, the ductility, the fatigue performance can be very good. So the benefits to DoD are obviously repair. That's the biggest benefit we see today, but also surface modification for enhancing performance. That's a big factor going forward with some of these materials we're developing, especially these chrome and nickel replacement type materials. We're finding that they are not only a replacement for wear and potentially a corrosion barrier, but also they're excellent in things like impact resistance and so forth. So cost savings, logistics reduction, all of these are big benefits that we're currently seeing across the DoD. And as this rolls out to more depots, shipyards, and so forth, we expect these advantages to grow. So with that, I'll take any questions that there are.
Great. Thank you so much, Aaron, for a fantastic presentation. We have received a number of questions for you. And we'll start with one from Lockheed Martin. What are the technology challenges that constrain cold spray adoption?
So there's not as many technology challenges as there are, I would say, I want to say political challenges, but there's mindset challenges to the introduction and the incorporation of cold spray. From a technology standpoint, we've been working with this technology for upwards of 2 decades now. We've got a lot of background knowledge on what needs to be done. The issues are really in changing the mindset of what is possible, and that's what we're trying to do as we go forward. So I guess, you know, the biggest technical hurdle right now, if I was to down, would be the use of helium versus nitrogen. There are some people that are reticent to use helium because of the cost, and there, I guess the big factor is you've got to analyze the total cost of repairing the part. So it's, yes, the cost of helium per cubic foot is significantly more than nitrogen, but if you look at the overall cost of the process, and if you start to incorporate things like helium recovery, which we've developed over the years, you can bring those costs significantly down.
Wonderful. Thank you so much, Aaron. This is a second question from the CIFCO Applied Surface Concepts. Is the bond strength test defined as an ASTM procedure, or is it a custom in-house process?
Sure, that's a good question. So a basis of that test is actually a mill standard that's used for evaluating the properties of a weld deposit. So it's actually created to evaluate a strength of a weld joint. We have modified that because we've you know, through finite element modeling and so forth, we've figured out that an undercut prior to the lug actually reduces the stress concentration, and you can get a more pure shear across that joint. We've also reduced it from what used to be a triple lug shear to a 2 lug shear, so that when you fail the first lug, you don't have to rub across that first lug to get to the second lug. That allows you to do a post-test analysis of the fracture surface to actually get a lot of useful information. So we've slightly modified it, but it's based on a mill standard for weld deposits.
Thank you. Can you tell us if there's a difference between the bonding mechanism between the deposit and the substrate versus between layers within the deposit?
Yeah, so the major difference there, I guess there's 2 really. The first is the substrate generally has a thicker native oxide. So the powder is pretty well controlled. We do a lot of work to prepare the powders in a dry environment, to manage them in vacuum bagging and inert packing and so forth, so that when they're introduced to the process, we can get you know, a good quality deposit. The substrate, you can do things like cleaning the substrate and so forth, but there's always a native oxide that's going to form on that surface, and that's probably the biggest challenge to you know, to bonding to that substrate. There has been a lot of work by folks at NRC in Canada, actually, to look at ablation of the surface of that substrate with a high frequency laser to disrupt the oxide just ahead of the deposited material, and you can see a major difference in the bond strength and the quality of that joint. On the other side of things, you can also affect the powder you're using, the types of powders, the blends of powders, the chemistry of the powder, and so forth, to enhance the bond so that you don't need that laser to achieve the same result. You can increase the amount of plasticity, like we were talking about in those early slides. It's that plastic deformation that's actually causing the bonding. So if you can increase that, you can achieve a very high bond strength. And then within the deposit, you have like on like materials, and you have very clean surfaces to bond to. So you don't need what you're doing at the interface. You don't need that anymore once you're within the structure of the coating.
Thank you, Aaron. This is a question from the University of Southern California. Can cold spray be adapted for less durable, non-metallic substrates such as polymers?
Yeah, that's a good question. We've done some work in polymer deposition, as well as deposition of metals onto polymers. Both can be done. There are slightly different bonding mechanisms when we start talking about very different materials. Like if you're trying to put polymer on a metal or metal onto a polymer, there's much more mechanical interlocking that needs to be done than metal to metal. In a metal-metal joint, you're getting a metallic bond due to that cold welding. You don't get exactly the same thing when you're putting like a polymer onto a metal. Polymer on polymer, however, you do get a very good bond because of that plastic deformation. So the polymer buildup itself can be very good quality, and if you're building it up on a polymer substrate, you can achieve very good qualities as well.
Great, thank you. What other non-destructive testing techniques have been evaluated for cold spray, either by you or by others?
Yeah, so certainly for bulk deposits, people have used things like CT scans to evaluate the material. The types of defects that are in the structure don't have a lot of volume to them. So CT scans, it's a very big challenge to try to find those types of defects. Pores, yes, you can find porosity in the structure, but when you have a closed shut defect, that's going to be a challenge to find. Conductivity has been our best approach so far. We're looking in more detail right now at UT, and there has been some work on Barkhausen in the past, I believe. I don't have the details on that, but I can certainly dig them up. If anybody is looking for that information, you can contact me at the email address.
Great, thank you. Another question that has come in, it relates to emissions. How does the cold spray repair process impact emissions to the environment? And is there chrome in the powders used for the wear coatings? And does that impact emissions?
Right. So the process itself uses inert or semi-inert gases. So the emission of nitrogen to the atmosphere is not an issue, helium is not an issue, and air, of course, is not an issue. So really, it gets to the powders themselves. When you're dealing with powdered metals like this, the constituents within that are all in metallic form. So there's no ionic species, nothing of that sort that can go into a stack, for instance. So what we're looking at is solid particles and their metallic particles. So HEPA filtration takes care of even the finest of those particles, and the filtration systems that are used to evacuate a booth during the process are 99.999% efficient. So they're very highly efficient at capturing any dust that is created from the impact process.
Thank you, Aaron. One more question for you before we pull Frank and Mark into this Q&A session. This is from United Technologies Research Center. Are there corrosion performance data available for these cold spray repair process coatings, particularly the galvanic corrosion resistance substrate?
Sure. So there is data that is now being generated. I guess I don't have data that I can show yet. I can share it potentially offline. We're just starting to get some data in specifically to the materials that were developed for ESTCP. These are the chrome and nickel replacement materials, and how they act on a steel substrate, for instance. So as an example, for the armor application, that's a steel substrate, and we want to be able to protect the material from future corrosion. So we did do both potentiostatic type tests as well as salt fog type tests in collaboration with Penn State University. So we have some of that data. We're generating more of it as part of our ESTCP program. We're in year 2 of that program. By the end, we'll have significantly more data.
Great, thank you. All right, well, let's go ahead and pull Frank and Mark back in. I have a few questions for them, and then we'll wrap up with you, Aaron. Frank and Mark, what percentage of metal working fluids do you avoid by using the technology you described, the Waterjet technology?
Well, that's a great question. Most manufacturing facilities, they live on metalworking fluids that's mostly chlorinated. We buy probably thousands of gallons here every year. We have a company that they pay to take out chlorinated and hazardous materials and fluids. With the adoption of the Waterjet technology, we most likely can avoid 10 to 20% with the cleaning and the machining technology over the processes that are currently in place. And that doesn't include the stripping. Mark can talk about what's involved in the stripping of barrels when the reverse electroplate occurs. Do you have a handle on what would be avoided on that process?
A normal reverse electroplating process, it's a plating process. You're just reversing, but you're still going to be doing the electrocleaning, the electropolishing, and all of that. And you try to avoid that if possible, because again, you're exposing workers to, nasty environmental chrome issues, and this would replace all of that. It's just having to strip the coating off instead of having to reverse electroplate it. It really is a no-brainer in terms of chromium to remove the chromium from a barrel. The environmental aspects alone.
Great point, Mark. And we often don't talk about user exposure and the permissible limits, which are really in the highlight and the key why hexavalent chrome should be avoided, because those they've been eliminated, I believe, in the European Union. They've been a tremendous thrust for trivalent chromium, which the jury's still out on that. There's been a lot of data generated throughout ESTCP and SERDP on trivalent technology. It's slow to adoption. Whether it be good for the protection of high temperature, that would be forthcoming. But the waterjet technology certainly protects the environment and also avoids exposure to workers.
Yeah, because when you strip the coating, it's in the metal form, and that's not an environmental hazard. That can just be filtered out at the end of the process. You know, the chips or whatever comes off. I mean, that's not, chromium metal is not hazardous. So it's not a plating process, which now you're concerned about, you know, workers breathing fumes in and stuff like that. And this avoids all of that.
And that might lead to the second question, what do you do with the chips? And we certainly can filter them out by either hydrocyclone or another method of classification. And
they could be recycled, they could be sold. I mean, there's a lot of things that they could do.
They have recycling value after they're stripped.
Great, thank you both. And a question for Aaron, and let's talk a little bit about cost and quality. What is the difference in cost and quality for the wear coatings spraying with nitrogen versus helium?
Yeah, so with nitrogen, we can achieve certainly all of the lower hardness materials. So all the materials that are generally used for replacement of nickel are very easy to spray with nitrogen. So that's the WIP C1, the WIP C2. Those are straightforward spraying with nitrogen or helium. When you spray them with helium, you do get a slightly higher hardness and a slightly lower porosity level. But from a performance standpoint, there's only marginal differences. If you recall back to the chart I put up for the armor application, the differences between spraying with nitrogen and helium in V50 impact performance were very minor. With the higher hardness materials like the WIP W1, we're still finalizing our nitrogen spray parameters, but as it looks right now, we can achieve maybe a 100 Vickers drop in hardness with nitrogen as opposed to helium. So we are seeing about 100 Vickers loss in hardness. That will affect some wear applications, the ability to to have the highest the wear rates and so forth. So there is certainly that offset where you start to say, well, let me use nitrogen to build up the bulk of the thickness and then just top coat it with helium, for instance, to get me that best of the best performance on the surface. That's for those applications that really need the highest performance. Already that material outperforms chrome, so even with nitrogen, again, we're still collecting data, but we think even with nitrogen, we're going to be equivalent to chrome.
Great, thank you so much, Aaron. It is time for us to wrap up. But before we do so, I just would like to get your perspectives and your input on a last message that you would like to leave our audience with about reducing hazardous materials in weapons systems. And let's start with you, Aaron. What is that last message that you would like to reiterate to our audience today?
Sure. So all manufacturing processes are going to create some sort of some sort of waste stream, some sort of emission, or whatever. And I guess the biggest thing I can say is cold spray as a process can achieve two major goals, at least two major goals. One is to be a direct replacement for those more environmentally unfriendly processes like chrome and nickel electroplating. But it can also keep parts in the field longer, eliminating the need for manufacturing new parts. Because as I said, all manufacturing processes, if I've got to make a new part and I add up what it takes to cast that hunk of metal and then forge it and then go through the machining process and so forth and so on, I'm going to be creating a waste stream the whole way. I can avoid all of that by simply repairing the part and putting it back into service. So those are really the two big areas that cold spray has a huge advantage.
Thank you, Aaron. Frank and Mark? Maybe we start with you, Frank.
Go ahead, Frank.
Well, I'd just like to say, really, on the coattails of what Aaron stated, is that these processes are truly the lowest impact to the environment, as we demonstrated with hexavalent chromium and short chain chlorinated paraffins, reducing the usage, user exposure, minimizing that, and I think that sort of wraps it up. On your end, Mark?
Yeah, I would add that Waterjet, is also going to allow for the successful use of other refractory metals on weapons, like they're currently being classified now in the smaller caliber arena with, Picatinny and Art Aberle now helping to adopt this for the smaller caliber. And it will allow for cleaning and stripping of weapons, and which is a huge environmental plus. The Waterjet has a future, and it modernizes the Army when it comes to weapon system platform.
And in conclusion, we also work with the NDCE, another DoD group, and we are looking at alternative three-dimensional machining technology with Waterjet, and just in lieu of cutters and metalworking fluids. So I have to mention that because they've funded us over the past 2 years.
Wonderful. Well, thank you to the three of you for a very engaging webinar. At this point, we're going to go ahead and wrap up and remind you all that our next webinar is on Thursday, September 24th, and it will feature results from DoD-funded research efforts to model munitions, mobility, and burial in underwater environments. Our speaker will be Dr. Joe Calantoni from the U.S. Naval Research Laboratory, and he'll talk about field and laboratory experiments performed using surrogate and inner certified munitions in underwater environments. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. As far as webinars in the WP program area, there are two joint WP-ER webinars on October 8th and 22, as Tim mentioned, and they'll focus on AFFF impacts to groundwater and treatment technologies, but the WP projects will feature alternatives to fluorine-free foams. Before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your time.
Thank you.